Okay, so thank you very much for this invitation, and I wish to thank also Sylvain Boulet for the invitation for this lunar marathon. A few years ago, we participated with telescopes, and this time we participate with talks. But it's always great to be here again. So today I will talk about the regolith, and in particular of the moon regolith, of course. But I will, at the end of the talk, I will also compare it with our knowledge of regolith on other small rocky bodies, essentially asteroids, which is more my expertise. So the lunar regolith is, as a matter of fact, a very fine material. It looks like essentially with powder, I would say, that covers the entire moon, the entire surface of the moon. It comes from two Greek words, regos and lithos. It means like a blanket of small fragments, or blanket of rocks. And we'll see that it is essentially very thick. It's about 5 meters thick in the regions where the Maria are, and it can be even thicker in the lunar highlands, which are older and have been more processed. If we take from NASA some information, we can find out that the regoliths, that the particles, that make the regolith, are essentially very small. They are essentially smaller than 1 millimeter. 50% are, let's say, about 100 microns, so 0.1 millimeter in size. And a lot of them are even smaller. They can go back to, let's say, a few tens of microns. And so here we see a picture where the famous astronaut footprint into the lunar regolith. So it's like flour, I would say, but it's very abrasive and it sticks to the astronaut boots. So here we see how is a cartoon from the very important works done by Professor Friedrich Horst and his colleague like Basilewski, and more recently to Ottaviano Ruesch. But it's clear that the moon regolith form in the following way. So essentially, when a big meteoroid, it's like a little asteroid, hit the moon at several tens of kilometers per second of speed, it can penetrate the regolith, which is, as I said, meter in thickness, and extract from the underneath bedrock blocks, like boulders, like big rocks, and that are deposited on the surface on top of the regolith. Because they eject, they fall back. And very gently, the micrometeoroids, which are smaller meteoroid, I would say, they essentially sandblast these, they break and sandblast these blocks to comminute them into very, very small particles until they diffuse into the lunar surface. And this is how we understand that the regolith is formed. As we will see, we have regolith essentially on most of the solar system rocky bodies, including Earth, of course, and it covers several asteroids. But in the case of asteroids, it's not only the impact of micrometeorites that create it, but there are other effects that I will show at the end of my talk. And here you see an old photo from the Apollo mission of a tiny crater that is several meters in diameter, from which we start to see blocks extracted of several tens of centimeters, extracted from the bedrock underneath the regolith. So it's not only a theory how the regolith form, but the crime scene is very clear. So this, for a geologist, a geomorphologist, which is not me, but they are expert on this, they clearly understand from these images how the regolith is produced. And we have now exquisite surveys that provide amazing images of the entire lunar surface, such as the NASA Lunar Reconnaissance Orbiter, or LRO. And my colleague, Ottaviano Ruesch, is now in Germany, he looked at many rocks on the moon, observed from LRO, and he classified them, and he noticed how they break. And here we see like a few images of his publication in 2020, last year. And there are many ways they break. They break with fractures, with multiple fractures, but it's clear that most of them, they go through an in situ fragmentation. So the micrometeorites, essentially, they break these rocks in place, and essentially they destroy, they sandblast until they become regolith. It's very interesting that the regolith presence on the moon has been understood much earlier than the space missions. Essentially from telescopic observation by the heat emitted by the moon. And for instance, we know that rocks cool very slowly, whereas sand or powder cools very rapidly because it has very low thermal conductivity or thermal inertia, the capacity of a material, the property of a material to keep up with temperature changes. So if you observe the moon, the heat emitted by the moon, it's very hot, the moon, because it's illuminated by the sun. When it's illuminated by the sun, it can reach 100 degrees Celsius. But if we had a way to block the sunlight, we would see that the lunar surface, we could study how the lunar surface cools. And this is exactly what they did, these gentlemen. You see the publication here in my slide. They waited for a total eclipse of the moon when the moon enters the Earth shadow, and they looked how the moon cools. And here are images from their 64 paper of Seri and Shorthill, and they show that you see on the top the images light, visible light, and on the bottom the thermal infrared light, so the heat emitted from the moon. And they saw that when you get into the umbra phase, essentially the moon cools very quickly. And this means that there are essentially very, very few rocks, essentially no rocks on the surface. It's like when you're at the beach and it's a sandy beach, as soon as the sun goes down, you feel your feet cold. Whereas if you are on a rocky beach, like here in Nice, you have more time to feel the cold of the night because the rocks keep up with the temperature. Modern observations of the moon shows much more details. And for instance, this can be done with a small infrared camera. They are expensive, but something you can almost have, very simple equipment. You can take this beautiful picture, thermal infrared of the moon. Or you can use a very sophisticated telescope like Paul Hain, that is a colleague of mine in Colorado, did. And they can actually monitor very well details of the moon while the moon cools during the lunar eclipse. And this is what Paul and colleagues did with the EOS infrared telescope. They saw these beautiful images of the craters where we see the rim of the crater that is still hot during a solar eclipse, whereas the bottom of the crater is much cooler, and the surrounding of the craters where regolith is filling the surface is essentially very, very cold. And so this shows that what I described before, the craters are the place where the blocks, new fresh blocks, come out, and then they are grinded down to form a new fresh regolith. This process takes millions of billions of years. It's not something very quick. This is a map from Paul Hain et al. This shows how much rocks are on the surface compared to regolith. And we see that it's very, very little. Even the rockiest point on the surface, which are these craters like Tycho Brahe, Copernicus, Giordano Bruno, and so on, they have only a few percent, 10% of rocks on the surface. And if one pay attention at the idea, the paradigm of rock formation, can really understand, can really imagine there should be a correlation between the amount of regolith present at the craters and their age, and exactly what happens. This publication, another publication from the Paul Hain on the left, this shows the thermal inertia. This is a proxy for thermal conductivity of craters of different ages. So you see that a young crater, only Giordano Bruno, is about 4 million years old, is very high thermal inertia, is white in this picture, which means there's a lot of rocks. Whereas Copernicus, that is almost a billion year old, it's almost 800 million years old, is essentially very, very little rocky. And another colleague, Rebecca Gent, put this in a nice diagram showing the rock abundance, how much rock abundance is present on the moon near craters of known age. And we can clearly see that if you plot the logarithm of the rock abundance as function of the logarithm of the crater age, you essentially get a beautiful line. So this means that the rocks, the abundance of rock, the rocks are really grinded down as the surface ages with time. Essentially, when you are a billion year, the surface that is a billion year old, there is very, very little rocks, big rocks present on the surface. This is essentially fine materials. But the impacts on the regolith on the moon do not only extract blocks to be grinded down by micrometeorites and form fresh regolith. Small impacts, we will hear tomorrow about this from the talk of Krista Avdelido, that she will show what happened when small meteoroids hit lunar surface with telescopes. But what we see on the moon is that these smaller impacts, when they hit the regolith and not the blocks, they can actually melt the regolith and make what we call the agglutinates. Essentially, they fuse the regolith, they make a sort of glass, which can incorporate particles that are not fully molten. And these are images of an agglutinate that I took from a website of NASA, but it clearly shows what we are talking about. It's a glassy stuff with little particles lithologic particles or rocky particles inside. And when the micrometeoroid is even bigger, so deposit more energy into the regolith, it can create new rocks. And these are not rocks that come out from the bedrock of the moon, but is regolith compressed by an impact to form a rock. And we call them regolith breccias. We also see them on asteroids. So essentially what I described, this is a type of breccia that is, I would say, different pieces of material glued together, welded by the heat of an impact event from a meteoroid that hit the surface of the moon. Now I will change pace and I will move further away from the moon just to compare what is our knowledge of regolith of the moon compared to other rocky bodies. And I will focus on asteroids, on rocky asteroids. And it's interesting because the first infrared data from asteroids, they show a relatively low thermal conductivity, as the case of the moon. That was, we didn't see eclipses on asteroids, but there are other ways to study these things. And so it was understood that asteroids also have regolith. And here is an example. This is 433 Eros, which was visited by the near Shoemaker NASA mission, which eventually found his, let's say, grave landing on the surface of Eros. And to the right, to the left, we see the picture of the entire asteroid. And to the right, we see a picture of the region where Near landed and let's say crashed more correctly. And we see that there is a lot of fine material that is about a millimeter in size. So is coarser, is much coarser than the regolith on the moon. And if we go to smaller asteroid, this is the asteroid Itokawa that was visited by the JAXA Hayabusa 1. And we see that is a much smaller object. This is only 300 50 meters equivalent, so it's like 500 meters in length. There is almost very little regolith. It's a blocky surface full of big blocks, like meters in diameter. And we see that the regolith is confined in these two areas, which I have encircled with red lines to draw your attention to them. These are similar, let's say they are the potential lows, is where the gravity tends to push all the material. And even more dramatically than the case of Eros, the regolith on Itokawa is very coarse. So it's like a centimeter size. It's like, it's not like a sandy beach, but it's pebble size, like centimeters. And to the right, we see the closest images returned by Hayabusa #1, which is called Hayabusa, which, by the way, it sampled the asteroid and returned a sample back to Earth. So everything was, we thought to understand these things, and until last few years, we adventure ourselves to study another class of asteroids, which are called the C-type, the carbonaceous asteroids. And to the right, you see an example. This is the asteroids Bennu, which has been studied in details by the NASA OSIRIS-REx sample return mission. By the way, OSIRIS-REx captured a sample from the asteroid and is now on its trajectory back to Earth. It should be arriving to Earth in little less than 800 days to return these precious samples into the American deserts. And NASA will go to collect it. So Bennu was a surprise, and because from telescopic observations, we understood the heat emitted by this asteroid, and we saw that these asteroids heat and cools very rapidly, like not like the moon, a little slower, but still quite rapidly to be a rocky body. And we thought that there will be a number of papers published that this asteroid was smooth, had a smooth surface covered by fine regolith, so centimeter or even fine regolith. And to our big surprise, where the first images returned in December 2018, when OSIRIS-REx arrived there, and he showed the picture that you guys see on the right here. It is a very rugged surface full of boulders, blocks of all possible diameters, ranging from tens of meters down to half a meter, I would say. But there is very, very, very little amount of fine regolith. We think that actually the fine regolith is present, but is in between the rocks. And there are more studies going on these things. And please stay tuned, because there will be papers coming out on these things in the future. In particular from the sampling, because from the sample, we see that there is regolith moving around. But it's very, very, essentially very little. The same story, these are close-up images of these boulders on Bennu. And here, the smallest thing you see, they do a few centimeters in pixel, but essentially there are no fine materials on it. Very interestingly is that these rocks, they cool rather quickly because they are very porous. They are nothing similar to what we have on the moon, that are hard rocks, but they are very, very porous. So probably they're very fluffy, I would say. The same story came actually a little earlier than Bennu, but since from the observation of another asteroid that is carbonaceous, this Ryugu, that shows the same story. So here is another object that is very similar to Bennu, is less hydrated, there is less water in the silicates, but in the phyllosilicates, but it has big blocks on the surface. And again, these were the first paper published by colleagues Matthias Groth, Tatsuo Okada, Seiji Sugita, and so on. And they show that these rocks are very weak and porous. And I conclude in 1 minute. You probably make me 30 seconds more, if I'm allowed, by showing how we make these rocks, how we make regolith on asteroids. Is not only impacts of meteorites, but is the tremendous temperature variation on this asteroid. Here you see to the left a temperature variation as function of time measured by Rositis and colleagues on asteroid Bennu. And you see there are almost 80 degrees of change in a few hours. And we reproduce this variation in the lab, and we subjected meteorites that are typical present on these asteroids, carbonaceous, to this temperature variation. And we looked at what happened to them. And we noticed in this particular region, these samples make about 2 centimeters in length. So the region we are looking at is the red region is about 0.5 centimeter. We saw that as the time goes by during temperature cycles, the cracks grow. And there is fracture widening, lengthening, and so on. So this process can actually produce particles from what we call thermal cracking. So oscillation in temperature can damage the rocks and break them to make a regolith. We think this process is important on asteroids because they spin very rapidly, whereas it's less important, or probably much less important on the moon. I think I can stop here, and I will leave you with these conclusions. And just saying one word is that the regolith is very important because when we try to understand the body underneath, we essentially study with telescope the regolith. So if we want to understand these celestial bodies, we need to understand the regolith. I can stop here and you can read yourself my conclusions. Thank you.